We've talked about water being amphoteric. It can act as either an acid or a base. And what it can actually do is it can act as an acid and a base with itself. And this is called auto-ionization, self-ionization. So 2 water molecules. One can act as an acid and donate a proton to the other water molecule, which is acting as a base. And you can end up with hydronium ion and hydroxide ion. Does that seem a little wrong? It does seem a little wrong, because why would one water molecule want to donate while another one wants to accept? That just seems a little weird, right? Well, it doesn't happen a lot, and this equilibrium lies far to the left. The equilibrium constant for this equilibrium is quite small. So it doesn't happen a lot, but it can happen, and it's very important. So autoionization of water. So here we have that reaction again. To write the equilibrium constant for this, we're going to have the concentration of the products divided by, oh wait, that's a liquid, right? So that doesn't show up. So Kw has a special name. The equilibrium constant for this reaction is called the ion product constant for water. So it's the ion products. So you take those, the hydrogen ion, the hydroxide ion concentrations, you multiply them, and you're always going to get the same number at 25 degrees Celsius. The value is 1.0 times 10 to the minus 14. That's a number that you should remember. So in pure water, the hydronium ion concentration is equal to the hydroxide ion concentration. Because where did they come from? If we look at hydrogen ions instead of hydronium ions, they came from the same place, right? You're essentially separating a hydrogen ion from the water, which makes a hydroxide ion. So they have to have equal concentrations. So pure water, you've got equal concentrations. Their concentrations would be the square root of Kw, which is 1 times 10 to the minus 7. So that's a small concentration, 1 times 10 to the minus 7th molarity in pure water. Very small concentration. We talk about solutions being acidic or basic. Pure water is neutral because the concentrations of acid and base are equal. The hydronium ion and the hydroxide ion concentrations are equal. Any questions? So an acidic solution has more acid in it, right? It has an acid in it. The acid creates extra hydronium ions. Well, we had that, I'm going to write it out here because it's helpful to see it. Maybe I'll write it out. So we had this equilibrium, right? And so we've added an acid which creates a bunch of extra hydronium ions. Well, if we're adding hydronium ions to this equilibrium, what would Le Chatelier say? The reverse reaction is going to happen. If we're adding product, the equilibrium is going to shift to the left. What's that going to do to the hydroxide ion concentration? It's going to decrease it. It's going to get rid of some of the added hydrogen ions, but it won't get rid of all of them. But there's an equilibrium constant, Kw, for this reaction, and the equilibrium will shift so that Kw is always 10 to the minus 14. So you add acid to the solution, and you have a solution where your hydronium ion concentration is now greater than your hydroxide ion concentration. A basic solution, you've got a base that creates additional hydroxide ions. So essentially you're adding hydroxide ions. That also causes the reaction to shift to the left, reducing the hydrogen ion concentration. And so in a basic solution, your hydroxide ion concentration is greater than your hydronium ion concentration. But they are still related by the equilibrium constant, 10 to the minus 14. So calculate the hydronium ion concentration for each solution. Determine if the solution is acidic, basic, or neutral. So we're given hydroxide ion concentrations. We're asked to calculate hydronium ion concentrations. What's the relationship? They're not necessarily equal to each other, only in a pure water. But we have that Kw, right? Yeah, so we've got the hydronium ion, since that's what it's talking about, hydronium ion concentration times hydroxide ion concentration. And we know the value of that, 1.0 times 10 to the minus 14. So if we have a hydroxide ion concentration, what we're going to do is we're going to take Kw and divide by the hydroxide ion concentration, and that'll give us the hydronium. So this is going to equal Kw divided by the hydroxide. Yeah, 6.67. I'm going to round it to 6.7. Yep, times 10 to the minus 13. And the unit on that is molarity. So we've got a hydroxide ion concentration that is larger than the hydronium ion concentration. Is this solution acidic, basic, or neutral? It's basic. So this solution is basic. You have to get used to looking at negative exponents, because this exponent is larger, but it's negative. So this number is a lot smaller than this one that has the smaller negative number. Any questions about that one? What about this one? Hydroxide ion concentration is 1 times 10 to the minus 7. Yeah, so that must be a neutral solution. So if that's true, then the hydronium ion concentration also equals 1.0 times 10 to the minus 7. Or, you know, if your mind doesn't think of that, you can do this calculation. You're going to end up with the same answer. So this is then a neutral solution, right? Because the hydronium ion and the hydroxide ion concentrations are the same. So this one down here, hydronium ion concentration equals Kw over the hydroxide ion. So we take 1 times 10 to the minus 14 and divide by 8.2 times 10 to the minus 10. (1.2 times 10 to the minus 5). So here, the hydronium ion concentration is higher, so this is acidic. You can identify whether it's acidic, basic, or neutral without calculating the other concentration, because if this one is greater than a neutral solution, where it's 10 to the minus 7, then the other one must be smaller. So this one has to be basic, this one has to be neutral, that one has to be an acid, because here the hydroxide ion concentration is much smaller than a neutral solution. Any questions? So the pH scale. You should have heard of pH before. Anybody done pHs? Here come the logarithms again, right? Awesome. So the pH scale is just a compact way to specify the acidity of a solution. Because when we're talking about hydronium ion concentrations, they can range from like 10 to the 1 or 10 to the 0 down to 10 to the minus 14. That's 14 orders of magnitude. It's huge. A logarithmic scale compresses that. So pH means the negative base 10 log of the hydronium ion concentration. It's just the definition. Okay? So if we have a hydronium ion concentration that's 5.3 times 10 to the minus 8, and we want to know what the pH is. 7.27. Okay, 7.27.
Or 7.3.
So we put the concentration in there. We take the negative log. And I appreciate you doing that for me, but I still have to do it myself because I do.
Trust no one.
Yeah. Well, it's always good to do things twice, right? So my calculator shows me 7.2757, blah, blah, blah. Okay, so significant figures with logarithms. With logarithms, only the numbers to the right of the decimal point are significant figures. So the 7 is not a significant figure. Just the guys to the right are. So if our starting number, 5.3, has 2 sig figs, then I'm going to take this to the second decimal place, and it's going to be 7.28. And there's no unit or anything. That's just the pH is 7.28. So let's do one where the hydronium ion concentration is 5.3 times 10 to the minus 3. Then the pH is going to be 2.28.
I can't remember, isn't 7 neutral on a
pH 7.00 is neutral. Yeah.
Water, pure water.
Pure water, or you can have other stuff in there and it can still be neutral. So this would be very, very slightly acidic.
And anything above 7 is basic, anything below 7 is
Yeah.
acidic.
Yeah. Above 7 is basic, below is acidic. Did I get that right?
Yeah.
Yeah. So let's do, what if it was 5.3 times 10 to the minus 11? 10.28. I didn't use a calculator. No, I did not plan this ahead of time. So what is constant, what is the same, I should say, about these 3 concentrations? They're all 5.3 times 10 to the something. What's different is the exponent. Here the exponent's 8. The number before the decimal point is 7. Here it was 3, and now it's 2, 11, and 10. The number before the decimal point comes from the exponent. Those are all the place-holding zeros. The digits after the decimal point refer to this 5.3, which is our significant figures. Yeah?
There's an upper limit for what it really should be, right?
Yeah, there is an upper limit.
What's
So
that?
typically 14 is considered the highest pH.
If something can't have a higher or smaller polarity.
Yeah, I mean, of course, you try to find situations that go past that. And it is possible to have a negative pH. Yeah. But typically we think of it as being 0 to 14. So the pH scale, 25 degrees Celsius. This is showing us the relationship between pH and the hydroxide ion concentration. And if you're dealing with like 1 times 10 to the 7 minus 7, then we see that pH 7 correlates to 10 to the minus 7. pH 12, 10 to the minus 12 for the hydrogen or hydronium ion concentration. So below 7 is considered acidic, above is considered basic. So here we're asked to calculate the pH of each solution, indicate whether it's acidic or basic. So the first one, we're given hydronium ion concentration. So pH is negative log of 9.5 times 10 to the minus 9. This is going to be 8 something. 8 point what? 02. So 8.02. Our concentration had 2 sig figs, so we want 2 decimal places in our pH. Yeah.
So the whole number is always 1 less than the exponent?
Yes.
Okay.
Yep, the number in front of the decimal point is going to be 1 less than the exponent.
And then according to the last slide, just looking at the 10 to the negative 9, you already know it's going to be basic.
Yeah. So we can look just at this concentration. The hydronium ion concentration is less than 10 to the minus 7. So we know that this is a basic solution. And we calculate the pH. We see it's above 7. And so this is definitely a basic solution. So here we're given the hydroxide ion concentration. And they want the pH. We can look at this and identify whether it's acidic or basic. What is it? It is not acidic. It's basic. Because this is hydroxide ion. So the hydroxide's high, that's the base, and the hydronium must be low. So this is this is also basic. So to get the pH, we need to calculate the hydronium ion concentration first. Right? So we've got 1 times 10 to the minus 14 divided by 7.1 times 10 to the minus 3. And then we're going to do the negative log of that. So this is giving me 1.4. We got 2 sig figs here, but I'm going to carry 2 extras because I don't want to have rounding errors. And this is 10 to the minus 12. So then the pH is the negative log of that. It's going to be 11 something, isn't it? $11.85. Any questions? Yeah.
Isn't there like a circle or something that?
There is a circle. We're going to come to it. Yeah. We'll get to it in just a minute. Yeah.
Didn't you also just determine the pH by just taking the concentration of the hydroxide and just 14 minus the 2.8?
Yes, you could.
Because it has to equal 14.
Right. Yeah, we'll do that too. You guys are thinking. Any other questions about this? What if we're given the pH and we want to calculate the hydronium ion concentration? So we're going to have to do inverse logs, right? So we know that pH is negative log of hydronium ion concentration. So we need to rearrange this and solve for the hydronium ion concentration. So there's this negative here. So let's multiply both sides by -1. That makes this positive and that negative. And then to clear that logarithm, I'm going to take 10 to the x of both sides. So I get 10 to the x, 10 to the negative pH is going to equal the hydronium ion concentration. So the hydronium ion concentration is 10 to the negative pH, 10 to the negative 8.37. And yeah, we don't usually do decimal numbers as our exponents, but your calculator's fine with it. Just make sure to get the negative in there. Now, when I do this on my 36X Pro in decimal notation, it gives me a bunch of zeros and a 4. Does that mean that there's no digits after the 4? No, it just means that it had enough space to show me that first digit, and so I thought, well, that's good enough. No, it's not good enough. I've got to put it in scientific notation for stuff like this. So it's actually 4.2657 blah, blah, blah times 10 to the minus 9. The unit's molarity, how many significant figures should that number have?
Three past the decimal.
The pH, only the numbers after the decimal point count. 2. So the 3 and the 7 are what give us the 4.26 business. The 8 comes from the 9. So we would express this as 4.3 times 10 to the minus 9 molar. Any questions?
Why is it only 4 point? Oh, because it's 3.7 says 2 sig figs on the other.
Yeah, so there's only 2 sig figs in here because this is the 10 to the, it's the decimal holding zeros business. The 3 and the 7 are the significant figures, so we only keep 2 here. I'm not going to try to trick you on that, but at this level of chemistry, you should be able to handle that and at least get close, right? Well, you can do pH. You can do P of other things. So we have other P scales. You can talk about POH. So this is with respect to hydroxide ion concentration. So POH is the negative base 10 log of the hydroxide ion concentration. You can do P calcium. It's the negative log of calcium ion concentration. So P is a mathematical operator that means negative base 10 log of. So we can also have, we've got the Ka, that acid dissociation constant. We can also have pKa, the negative log of the acid dissociation constant. When we're looking at POH, we see that things are just opposite, right? As the POH gets lower, it becomes more basic. With the pH scale, as the numbers go higher, it becomes more basic because they're inversely related to each other. So let's derive the relationship between pH and POH. Well, our starting point is going to be that relationship where we know that Kw is equal to the hydrogen ion concentration times the hydroxide ion concentration, right? And that equals 10 to the minus 14. Well, if we want this to be logarithms, then we need to take the log of stuff, right? So if we take the base 10 log of both sides, the log of 10 to the minus 14 is what? It's minus 14. The base 10 logarithm asks, what is the exponent of 10 that is equivalent to this number? So 10 to the minus 14, the exponent of 10 is minus 14. If you have 1,000, the log of 1,000 is 3, because it's 10 to the third. So the log and the 10 to the x, log and anti-log, they cancel each other out, another way to think of it, so that's minus 14. Okay, so when we take a logarithm of numbers that are multiplied, that is equivalent to the log of each of those individually added. So the logarithm business is not going to go away, and so if you're fuzzy on this, you need to review your math. Okay, so we still don't have pH or POH in here at all. Let's multiply both sides by -1. I don't like that negative over there. So this is going to become negative, and that's going to become negative. What does this equal? Negative log of the hydrogen ion concentration. pH. What does this equal? Negative log of the hydroxide ion concentration. POH. And what does 14 equal? 14. There you go. pH plus POH equals 14. That's a useful little equation. Any questions? So that brings us to the circle of life, no, the circle of pH that Annette was asking about. So let's put pH up here, and I end up drawing this like differently quite frequently. So let's see, pH. We'll put hydronium. I'm just going to do hydrogen ion concentration over there, and hydroxide ion concentration down here, and POH over here. So these are the four quantities that we've been messing around with, right? They are all related to each other. You can convert between pH and hydrogen ion concentration. You can convert between hydrogen ion concentration and hydroxide ion concentration. It's trickier to go from pH to hydroxide ion concentration in one step. Now, is it theoretically possible? Of course. Is it worth learning how to do? No, because you can just go in two steps that are easy. So the relationships here between pH and hydronium or hydrogen ion concentration, we've got the definition of pH, that's for going one way, and then the hydrogen ion concentration is going to equal 10 to the minus pH, that's for going the other way. Then we've got Kw for water. So we know that those concentrations must have a product of 10 to the minus 14. Over here, these are the same as on the other side. Negative log of hydroxide ion concentration and the hydroxide ion concentration equals 10 to the negative POH. And then we have that little joule that we just derived, pH plus POH equals 14. And that is the circle of pH. Yeah. What do you mean by will we be doing this on the exam? Will I be given the circle? Will I give you the circle? Absolutely not. No. These are relationships that you need to know. And it's really not that hard. Now, you can come in to take the exam, and before you look at the questions, because as soon as you look at the questions, you lose your mind, right? You forget everything. Before you look at the questions, flip the exam over, draw this on the back. That's fine. You brought it in your head. You just, like Dumbledore, you pulled it out of your head and put it on the paper before it could get wiped away, right? So any questions about this? So you can convert any of these things in the circle. And one person might do it differently than another. I have my favorite directions to go. You may prefer other ways, but we should get to the same answer